3, 2, 1, and away we go. A brand new era here in our 2070 online videos for matrices and linear algebra. And so we've been hanging out with eigenvalues, and now we're going to shift gears and get a little bit more geometric, as you can probably read from the title here. Obviously, the word length and orthogonality is showing up, so probably going to be a little bit more geometric. So speaking of geometric, let's just go ahead and draw a picture in R2. Ooh. So if I pick an element in R2, it has a first component, it has a second component, and if I want to, I can draw this on my usual x and y axis. And note here that the length of the vector x, well, that's this diagonal of this rectangle, and we know that to get this length here, by the good old Pythagorean theorem, you would do the square of the base, which is x1, plus the square of the height, which is x2, and then take the square root of that. So the length of this vector should be that quantity right there. So there's picture worth 1,000 words. Okay, so our first goal is going to be to extend this definition to all of Rn, not just R2 or R3, but all possible Rn's. And obviously we want a little bit more context. We don't want to just sort of copy this formula and just let it go to Rn. Why is this the right formula, and what are some maybe more useful algebraic tools associated with it? Alright, so indeed, given two elements in Rn, we're going to create their dot product, or their inner product, to be as follows. We match the components, we multiply them together, and then we add them up. So in our previous video, we were talking about the complex plane, where you can equip R2 with a multiplication. That is a little interesting. Here we have the dot product, which is a little interesting on its own as well. As we'll see, it's very useful. And note that it is computed by taking your components, matching them up. So match 3 and 6, match -1, -2, match -5 and 3, multiply them, add them up. There you go. And so then the length we'll define to be the square root of x dotted with itself. Now note x dotted with itself is the sum of the squares, and oh hey, we saw that in R2. And we'll take the square root, and there are reasons for the square root being taken. Obviously in R2 we see y, but for Rn there's good reason to do so as well. Alright, so extending the definition of length in R2 to Rn, I can compute the length of a vector in R3. So I picked 1, 2, -2, and I picked it because conveniently it has a nice length of 3. Of course, square root showing up is always a fun time, and by always a fun time I mean square root is a very useful function, but it also makes computations a little annoying, especially if this was like 8 instead of 9. Alright, but there's our introduction to inner products, and now, hey, we got a notion of length. You know what's really good about a notion of length? And before we get there, let's note dot products have a couple of algebraic properties that we're going to exploit. One is that dot products are commutative. Dot products distribute the way you want them to. And scalars can be moved in and out as you please. One thing about dot products that's worth stressing, though, is that there's no associativity, right? There's no way to dot 3 vectors, because once you dot 2 vectors, you get a real number, and you cannot dot a real number with a vector. Alright. So we're going to make use of these, and we'll see in a moment where these get used. But as I was saying, let's draw another picture now. There you go. So if I have a vector x and a vector y, then using some vector knowledge, I know that the vector that starts at y and ends at x's tip will actually be x minus y. So that's the one of the diagonals of the parallelogram you can form using these two things. The other diagonal being their sum. And hey, the length of this, that measures the distance between my two vectors. So for any two vectors in Rn, we'll define the distance between them to be the length of x minus y. So for example, the distance between 10, -3, and -1, -5 is the length of the vector 11, 2, the other number. And then you can compute that and get 5 root 5. Of course, you didn't need to clean that up as much as I did. Root 125 is good enough. Alright. Hey, great, we've got a notion of distance. Beautiful. Now, before we move a little bit forward, it's worth doing the following calculation. So, previously, we outlined some basic algebraic properties of the dot product, and as I mentioned, the norm, or the length of these vectors, involves the square root, and then it ends up being that you'd rather deal with the square of them for the most part. And so the distance squared, which would be this squared right here, would be the dot product of u minus v with itself. And because we have distributivity and we know scalars behave, then we have good old FOIL at our disposal. So first, right there, outer, right there, inner, and last. Note, this is the length of u squared. That is the length of v squared. Oh, I had an x and a y, and they turned to u's and v's for reasons. Oh, boy. Oh boy, oh boy, oh boy. Oof, I'm a goof. Alright, I'll change the x and the y to u and v. That's quicker than changing the u's and the v's to x's. I don't know why the letters changed. Copy pasta. Good time. Alright, so, this calculation is actually going to be pretty useful for us, so keep it in mind for the very next slide. One last picture for today. Again, very geometric today. Let's say we're looking at this good old triangle here. You got an angle theta hanging out here, and you have a side A, a side B, and a side C. What law am I about to introduce? Alright, well, for the trig heads, you remember that the law of cosines ensures that for any angle, doesn't have to even be a right angle, there is a version of the Pythagorean theorem at our disposal. C squared indeed equals a squared plus b squared minus this part that shows up. Now, note that if I represent A, that length, as the length of a vector x, B as the length of a vector y, then C must be the length of their difference, because again, it's the distance between the two. Hey. And, oh, hey, this looks a hell of a lot like what we just computed. That right there. So, because we know that holds, matching it with this formula from the law of cosines reveals to me that the dot product of x and y has to be the product of the lengths, that'd be the AB right here, times cosine of the angle, right? Simply equating these two would force this and that to coincide. Now, note something. If we were in the Pythagorean case, where the angle was a right angle, pi over 2, the cosine is a big fat 0, which means, hey, look at that, the dot product is equal to 0 when I have a right angle, when my x and my y are perpendicular to each other. Oh, boy. So, wondering if my cat is right outside the door meowing. I wonder if it's picking up on the video. Leave a comment if you could hear the cat. Subscribe and hit that bell, bruh. Alright. So, in light of this, given vectors x and y in Rn, we say that they are orthogonal if their dot product is equal to 0. Right, because as we just saw, law of cosines revealed to us that this needed to be true, so this is what we'll take to be our definition of perpendicularity in Rn. Their dot products equal to 0. So, for example, these two vectors, 1, 1, 1, and 1, 1, negative 1, are orthogonal because their dot product is equal to 0. And of course, I got a text. This video is going good. We got typos, we got a cat. Wife's texting me about getting tattoos. You know, it's great. Alright. Sweet. Alright. Now that we have a definition of orthogonal, it's worth introducing a set we're going to play around with a lot in the next coming videos, and that's the orthogonal complement of a subspace. So given a subspace W, its orthogonal complement is the collection of things that are orthogonal to everything in W. Right, so formally we can write it out as follows in terms of the set notation here, but right, it's just the things that are all perpendicular to W. Now, this is going to be essentially a super abstract version of the normal line of the plane that you encountered perhaps in your Calc 3 days. And note something about this. if you take two vectors, x and y, that are in W, then scaling and adding them up and dotting them for any x, for any W and W perp. I'm missing a perp in there. Oh my god, this video is good. High quality content here. Okay. So, right, if given any x and y that are in W perp, well, then these dot products are going to have to equal 0, and there we see any linear combo remains in the set, so itself is a subspace. Well, if it's a subspace, that means we can find a basis for it, but how would you do that? Right now, this is kind of just an abstract idea, and sure, it's a subspace, and thus we can find a basis. How do you actually do this in practice? Well, it turns out that there's a pretty slick way of getting it if the subspace you're working with is a column space. Get ready, this is my all-time favorite formula in this class. And to get to it, we got to break down a couple of things. So if I take an m by n matrix A and I multiply by a vector x, well, then its jth component is equal to this. But now, in the language of dot products, note that this is the vector consisting of the entries found by taking the dot product of the rows of A with x. So if x is in the null space of A, that can only happen if all of these are equal to 0, and the only way that can happen is if you're orthogonal to all the rows. So, in other words, the orthogonal complement of the row space, the collection of all things that are perpendicular to the row space, is precisely the null space. Ooh, beautiful. And, well, let your mind note that I was talking column space initially. Well, remember, the row space of A transpose is the column space of A, and there we go. The column space's orthogonal complement is the null space of A transpose. This is my favorite formula because null space of A transpose, you pull the transpose out, but then you flip it when you pull it out, so you get the perp. Beautiful. Absolute great formula. Love it. And this always makes me think, like, this symbol for the orthogonal complement makes a lot of sense, right? Because it's the things that are orthogonal. Hey, it's like a right angle. T for transpose, though, like, the fact that, like, these flip into, like, it's so crazy as happens. This is, is it a happenstance that this just conveniently happened with the letters and symbols we choose, or was somebody being a little sneaky and they're like, oh, we should call this the transpose, because then the T flips? I don't know. Anyway, so here we go. If I actually want to compute an orthogonal complement, if I know it's a column space I'm interested in, I just got to characterize a null space. So if here's my matrix, and I want the orthogonal complement of its column space, I take its transpose, figure out the null space. I did it for you. It's 1, 1. That's got to be a basis for the orthogonal complement of the column space. Pretty cool. Alright, always love that result. It's a cool little one today to end the video on. Alright, so if that's... keep this stuff in mind, because the orthogonal complement's becoming our best friend in a little bit. Alright. Now, what's going to happen in the next video? Well, we talked about two things being orthogonal. How about more?